Hello and welcome. This video will be guiding you through an overview of the AMD Versal NOC-based hard DDR memory controllers. It will explore the architecture, configuration, simulation methodology, and hardware validation approaches for integrating and using DDR memory through the programmable Versal Network on Chip, or NOC. This is targeted toward engineers and system architects looking to optimize memory access on Versal devices. Let's get started. We'll begin with an introduction to the AMD Versal Programmable NOC and how it facilitates communication with hard DDR memory controllers. Then we'll cover how to configure the controllers in AMD Vivado Design Suite. From there, we'll dive into simulation and testing, both in software and hardware. Lastly, I'll provide some additional resources you can refer to after this session. The AMD Versal Network on Chip, or NOC, is a high-speed, scalable communication fabric that forms the backbone of data movement across the Versal architecture. It provides unified device-wide connectivity between all major IP endpoints. This includes the programmable logic, PL, the processing system, PS, hard IP blocks like DDR memory controllers, PCIe, and the AI engine array. It operates at up to 1080 MHz and uses packet-based communication, which allows for decoupled transactions and greater parallelism. The Versal architecture fundamentally differs from previous FPGA generations in that it requires all communication with hard DDR memory controllers to go through the NOC. This architectural decision improves scalability, data integrity, and performance predictability across the device. The configurable NOC is an AXI4-based network to route high bandwidth, real-time, and low latency connections. The NOC extends in both horizontal and vertical directions to the edges of the device. The multi-channel structures provide several options for routing and isolating traffic. The NOC is a full blocking crossbar between memory controllers, programmable logic, processing system, integrated hardware, integrated peripherals, and the platform management controller. Internally, the NOC transforms these AXI transactions into a fixed-width 128-bit packetized format. This packet-based protocol allows the NOC to route traffic efficiently across the chip using dedicated horizontal and vertical links. The ingress and egress points to the NOC are the NOC master and slave units, which provide asynchronous clock domain crossing, rate matching, and packetization from or to AXI3, AXI4, or AXI4 stream protocols, and the NOC packet protocol, NPP. The horizontal NOC, HNOC channels are located at the top and bottom of the device. They sit close to high-throughput peripherals like DDR memory controllers, PCIe blocks, and processing systems. The vertical NOC, VNOC, provides routing along the height of the chip. Devices can include up to 8 vertical NOC paths, which is determined by the die size and the number of hard blocks like DDRMCs. In AMD Versal SSIT devices, the NOC is extended between superlogic regions, SLRs using a NOC inter-die bridge, or NIDB. Together, the HNOC, VNOC, and NIDB form a fully integrated communication infrastructure, allowing the Versal platform to scale across device families and system requirements, while maintaining consistent, high-performance interconnect behavior. The integrated DDR memory controller is attached to the NOC interconnect. The controller supports both the DDR4 and LPDDR4 memory interfaces. It can be configured with a 32-bit or 64-bit DDR data interface with optional sideband ECC support. The DDRMC has 4 NOC interface ports to handle multiple streams of traffic and supports quality of service QoS classes to ensure appropriate prioritization of the memory requests inside the controller. A standard AMD Versal device can support up to 4 DDRMCs, while SSIT devices can have as many as 14. Depending on the DDR configuration, memory bandwidth can range from 6.4 GB per second to 34.1 gigabytes per second per memory controller. Selecting the appropriate mode and width is crucial for meeting design performance targets. In the AMD Vivado Design Suite IPI AXI NOC configuration wizard, the General tab allows the user to define the number of DDR MCs, AXI NOC master and slave units, AXI clocks, and inter-NOC masters and slaves, controller interleave size, the number of memory controller ports, the DDR address region of the controller. A single NOC instance can connect to 0, 1, 2, or 4 memory controllers, with interleaving enabled when using 2 or 4 controllers. When enabling memory controller interleaving, you must configure the interleave block size. This defines the number of bytes distributed per controller and must be a multiple of 128 bytes and fall within the range of 128 to 4096 bytes. The DDR address regions maps the memory controller's address within the unified system address map of the AMD Versal device. In the DDR Basic tab, use the controller selection dropdown to select the required controller type and clocking options of the DDR memory controller. Clock selection provides two options, memory clock and system clock. The memory clock period should correspond to half of the toggle rate of the selected DDR memory interface. The input system clock period is used to generate the clocking configuration and resulting memory interface options for the DDR-MC. The DDR Memory tab enables the user to select memory device types, speed bin, base component width, and memory device width. Device type allows the user to select the memory form factor of the device. Components UDIMMs, SODIMMs, RDIMMs, and LRDIMMs form factors are supported. SpeedBin allows the user to select a JEDEC supported SpeedBin for a selected DDR4 or LPDDR4 or 4X SDRAM controller type. The base component width defines the width of the die for the selected memory device type. Channel interleaving enables interleaving across two memory channels by automatically chopping AXI requests into interleave block size subrequests and alternatively sending subrequests to each of the two channels. The AXI NOC address mapping tab controls how AXI addresses are mapped to external DRAM address space. You can use default mappings or define custom ones. Custom mappings are powerful tools for optimizing row hits or managing memory banking, especially for workloads with predictable access patterns. QoS in the AMD Versal NOC enables reserving resources for critical data streams by assigning independent quality of service settings to each channel. These settings define traffic priority, such as low latency, isochronous, or best effort, along with bandwidth guarantees and latency requirements. By controlling these parameters, QoS ensures that time-sensitive traffic meets its delivery deadlines and prevents lower priority or high-volume transfers from starving critical flows. Simulation and testing are critical steps. Leveraging AXI performance traffic generators and AXI performance monitors enables evaluation of NOC behavior under synthetic and realistic memory loads. The AMD Vivado Design Suite simulation framework and integrated performance IP allow the user to measure latency, bandwidth, and verify functional correctness before going to hardware. AMD provides dedicated simulation IPs to help the user model memory traffic and evaluate NOC-based DDR performance without needing a full application in place. The AXI Performance Traffic Generator is the primary IP used to simulate memory traffic. It acts as a synthetic AXI master and is capable of generating a wide range of configurable AXI3, AXI4, and AXI4 stream transactions. This IP supports variable data widths from 32 to 512 bits, enabling the user to model memory traffic data. Complementing the generator is the NOC AXI Performance Monitor. This IP provides instrumentation to collect live statistics on the behavior of the NOC interface, specifically bandwidth in terms of read or write throughput, latency of individual memory accesses, outstanding transaction counts. These metrics help assess whether the NOC plus DDR configuration meets the bandwidth and timing requirements of the target application. They also help expose bottlenecks in interconnects, arbitration settings, and memory port usage. Together, the traffic generator and performance monitor form a powerful simulation toolchain that ensures the NOC and DDR MCs are performing as expected before moving to hardware testing. One of the first steps in configuring the traffic generator is selecting between synthesizable and non-synthesizable modes. The non-synthesizable version is used exclusively for simulation. It provides full flexibility to test and iterate traffic profiles rapidly. The synthesizable version, on the other hand, can be implemented in hardware, allowing you to generate memory transactions in real silicon for real-world performance validation. Next, select the AXI protocol type, typically AXI4 for memory-mapped transactions or AXI4 stream for high-throughput streaming interfaces. Additionally, configure the AXI data width, which can range from 32 to 512 bits. Choosing a wider interface, when supported by the NOC and memory controller, allows the user to increase throughput and better utilize the available bandwidth. Another key setting is traffic shaping, which allows the generation of more realistic workloads by controlling burst lengths, idle periods, and access frequency. The non-synthesizable version of the AXI performance traffic generator is designed specifically for simulation environments. It allows the user to test a wide variety of traffic conditions without consuming FPGA resources or requiring synthesis. It operates in two modes: fixed operating mode, where predefined traffic patterns are used, such as continuous reads, writes, or interleaved sequences. These patterns are ideal for stress testing DDRMC throughput and response time. CSV operating mode, which allows you to define a sequence of traffic instructions in an external CSV file. This is extremely useful for reproducing real-world scenarios, debugging edge cases, or exploring complex memory access sequences that would be difficult to implement manually. These modes help simulate everything from burst access to fragmented transactions, allowing fine-grained control over address sequences, timing, and burst lengths, all without leaving the AMD Vivado simulation environment. In CSV mode, you define memory traffic patterns manually, giving you full control over the structure and timing of simulated AXI transactions. This includes Traffic Generator ID. When using multiple traffic sources, each generator is uniquely identified. Transaction count and length. This defines how many AXI bursts are generated and how large each burst is. Access pattern. Whether the accesses are linear, ideal for large buffer reads, or randomized to simulate real-world cache miss behavior. Address offsets. These can be adjusted to avoid address collisions and to test memory interleaving efficiency across controllers. By tailoring these parameters, designers can model realistic traffic such as deep learning feature map access, video frame readback, or random access inference engines. These simulations provide valuable insight before committing to hardware. The synthesizable version of the traffic generator supports simulation and deployment in hardware. This is critical for validating system-level behavior under real operating conditions. You can use CSV mode similar to the non-synthesizable version to predefine instruction sequences. Dynamic mode, where the traffic pattern is loaded at runtime into BRAM using either a VIO interface or AXI4 Lite interface. This is useful for prototyping and in-field testing. Because the TG runs in hardware, it allows developers to validate memory controller bandwidth, latency, and arbitration under realistic system loads. The NOC AXI performance monitor is essential for quantifying how well your memory subsystem performs. It measures bandwidth in gigabytes per second or transactions per cycle, read and write latencies, outstanding transactions. The monitor includes up to 8 configurable slots, each of which can observe a separate AXI port. This means you can simultaneously profile access from multiple masters, like DMA engines, AI engines, or soft logic, and analyze contention. The monitor also supports trace and profile modes, enabling both cumulative data capture and cycle-by-cycle visibility. This makes it an invaluable tool when trying to identify bottlenecks, such as underutilized DDRMC interfaces, suboptimal interleave settings, or poor arbitration behavior. The AXI simulation trigger and clock or reset generator IPs are automatically inserted by the AMD Vivado during block automation, but understanding their roles is important. The simulation trigger synchronizes the start and stop conditions of one or more traffic generators. This ensures all test agents operate with coordinated timing, especially when running multiple TGs in parallel. The clock and reset generator provides domain-specific clocks to the AXI interfaces and DDRMC. This is especially important for matching real-world clock domains, including AXI4MM domains and memory PLLs. Without these components, simulation accuracy would suffer. Misaligned clocking or unsynchronized TGs could lead to incorrect latency measurements or misinterpreted traffic stalls. The following block diagram depicts a singular dual-channel LPDDR4 interface enabled with the NOC simulation, specific IP for simulation, and hardware testing. The AMD Vivado X-Sim simulator provides a full simulation environment where you can visualize signal waveforms, monitor latency, and generate performance reports. Bandwidth, captured via the AXI performance monitor and summarized in simulation reports. This gives you sustained and peak values in real time. Latency, observed in waveform views by measuring the delay from valid address to data return. This includes CAS latency, NOC arbitration latency, and DRAM refresh delays. Several real-world factors influence these metrics. Fall-through latency, which is the minimum response time without contention. Traffic patterns, such as burst length and address alignment. Page hit or miss ratio, which determines DRAM precharge overhead. NOC congestion, as the fabric is a shared resource and contention can reduce effective throughput. Together, these observations guide memory tuning efforts, interleave optimization, and application-specific buffer placement. Pin planning is a critical part of using the hard DDR memory controllers. The AMD Versal architecture requires DDRMCs to be assigned to specific I/O bank groupings, either double, 108 IOs, or triplet, 162 IOs, configurations. These groups correspond to physical DDR interface lanes and are tightly constrained. It's important to understand, not all I/O banks support DDRMC. For example, HDIO banks are excluded. The number of DDRMCs available is tied to the device package and footprint. Some smaller devices support only one or two. Incorrect assignment of pins or selection of unsupported banks will result in implementation errors or degraded signal integrity. The AMD Vivado Design Suite, Pin Planner and board-aware design flows help mitigate this risk. Once the design is synthesized and deployed, hardware verification is the final step to validate DDR controller operation. This can be done using XSDB or ChipScope in conjunction with the Performance Monitor IP. In real time, you can inspect AXI performance counters, confirm memory calibration and training success, measure sustained bandwidth and latency under live traffic. This hardware feedback is essential for closing the loop between simulation and actual deployment. For instance, if performance drops in hardware but not in sim, that could indicate contention, clock domain issues, or thermal throttling. Monitoring tools also allow you to check for corner case timing violations, which may occur under specific patterns or long-duration streaming use cases. The ability to analyze system health live without fabric re-instrumentation is one of the powerful benefits of using integrated DDRMC IP with NOC-based monitoring. The resources listed here provide additional support for implementing and optimizing NOC-based DDR memory designs in AMD Versal devices. The Versal NOC and DDRMC design process guide on the Xilinx Wiki offers in-depth explanations of memory controller setup, NOC routing, and system-level considerations. It includes detailed descriptions of interleaving strategies, address mapping schemes, and performance tuning. The AMD Vivado design tutorials GitHub repository contains practical, version-aligned examples for configuring AXI NOC and DDRMC blocks using simulation IPs such as the AXI traffic generator and AXI performance monitor and interpreting results from Vivado XSIM. These tutorials are structured to assist both new and experienced users in deploying high-performance memory systems. These resources are recommended for initial implementation, advanced performance tuning, and validation across all stages of development.